Okay, guys, let's go ahead and continue with where we left off in class. So I asked you to work through these graphing examples, and then this will be for you to check your work. Okay, so again, directions ask us to graph the function, determine the domain, range, and asymptote. So our base function here is the log base 4 of x. So again, if we want to sketch that graph, the 2 points on that graph are 1, 0, and then the base 4, comma 1. Okay, so graphically, our curve looks like that. And then we're just going to finish this graph off here using transformation. So there is a horizontal shift to be performed, so we're going to do that first. So that function would be the log base 4 of x plus 1, which would shift that graph to the left 1 unit. So again, a feature that we didn't mark on the first graph but we knew was present was the vertical asymptote at x is equal to 0. If we shift that left 1, that vertical asymptote is now at x is equal to -1. And then we take our 2 points, shift them 1 to the left. So the first point is at 0, 0. Second point is at 3, 1. And then we can go ahead and draw our graph like so. And then the last function we are graphing is the log base 4 of 1 minus x. So when we take the opposite of the x value, that's going to reflect the graph across the y-axis. So when we reflect that entire graph across the y-axis, the vertical asymptote is now at x is equal to 1. The point that was at 0, 0 stays at 0, 0. The point that was at 3, 1 is now at -3, 1. Okay, so graphically, our curve looks like so. And then we can determine the domain, range, and vertical asymptote. I'm going to write the domain and range in interval notation. So the domain would be -infinity to 1. The range is all reals. And the vertical asymptote is at x is equal to 1. All right, let's do the same thing for number 2. So our base function here is the natural log of x. So again, 2 points on the graph of that function are 1, 0, and then the base e, comma 1, which is like 2.7, comma 1. So graphically, our function looks like that. Okay, there is no horizontal shift to be performed here, so I'm going to work inside of the function. So next graph we're going to look at is the natural log of -x, which all I'm doing is taking the graph of the natural log of x and reflecting it across the y-axis. Okay, so the point that was at 1, 0, if I reflect across the y-axis, is now at -1, 0, and the point that was at e1 is now at -e1, so at -2.7, comma 1. Okay, so graphically it would look like so. And then the last thing for me to do here is to take the opposite of the entire function. So when I take the opposite of the entire function, we are reflecting the graph across the x-axis. Okay, so that's an x-axis reflection. All right, so the point that was at -1, 0 is still at -1, 0. But the point that was at -e, comma 1, when I reflect that across the x-axis, I'm taking the opposite of the y-coordinate, so that now that it is at -e, -1, or -2.7, -1. So graphically, my function looks like that. Domain, what x values get covered up? Well, they are from -infinity to 0. The range is all reals, and that has a vertical asymptote at x is equal to 0. All right, let's move on to 3. So for 3, my base function is the common log of x. Okay, so I'm going to show you a little trick for this. I don't want to make 10 dash marks going out in the x direction. Okay, so what I'm going to do instead here is I'm just going to label the coordinates of my point. So the first point is at 1, 0. Second point is at 10, comma 1. Okay, so again, I don't want to have to draw all those tons and tons of dash marks. Okay, so I'm just going to label the coordinates of the point. Okay, so again, no horizontal shift here, so I'm going to work from inside of my function out. So the next graph we're going to look at is the log of x over 2. So we haven't done this with like actual functions. We've talked about this, but we haven't done it with actual functions. So when I multiply inside of my function by 1/2, that's going to correspond to a horizontal stretch, which means, again, we talked about this way earlier in the school year back in chapter 1, which means we're going to multiply each x coordinate on our graph by the reciprocal of that number. So the reciprocal of 1/2 is 2. So when I multiply each of those x coordinates on our point by on our graph by 2, the first point is at 2, 0, and the next point is going to be over here at 20, 1. Okay, so again, that is going to be a horizontal stretch. Okay, let's multiply out front by 2. Okay, so 2 times the log of x over 2. When we multiply out front by 2, that's going to be a vertical stretch, so we're going to multiply the y coordinates of both points by that number 2. Okay, so the first point doesn't change location. It's still at 2, 0, but the second point that was at 21 is now going to be up here at 20, 2. Okay, so that graph is going to get vertically stretched by a factor of 2. Okay, and then the last thing for me to do is to take the opposite of the entire function. So when I take the opposite of the entire function, that's going to reflect the graph across the x-axis. So that first point at 2, 0 is still at 2, 0. But the second point, if I reflect that across the x-axis, I have to take the opposite of the y value. So that's now going to be at 20, -2. Okay, so graphically, my curve is going to look like that. Again, domain here would be x is greater than 0, so that's the interval from 0 to infinity. Range is all reals. And this has a vertical asymptote at x is equal to 0. Okay, last example. So y is equal to 2 minus the common log of x plus 1. So our base function is the log of x. I'm just going to go ahead and write out all the steps in order here. So the next function we're going to do is the horizontal shift. So the log of x plus 1. Then I'm going to do the vertical shift last. So the next function we have to graph is negative the log of x plus 1. And then the last function is going to be y is equal to negative the log of x plus 1 plus 2. Okay, so let's go ahead and work through these steps in order. So the log of x, again, I don't want to draw all those dash marks, so the 2 points are going to be at 1, 0, and then 10, 1. Okay, so graphically, our function looks like that. Log of x plus 1, that's a horizontal shift. We shift to the left 1 unit. So that's going to move the vertical asymptote to x is equal to -1. The point that was at 1, 0 is now at 0, 0. And the point that was at 10, 1 is now at 9, 1. Okay, so we're going to draw our graph like so. We then take the opposite of the entire function. So that's going to reflect that graph across the x-axis. So again, vertical asymptote is in the same spot. When we reflect the origin point across the x-axis, the point stays in the same spot. When we reflect 9, 1 across the x-axis, that is getting moved to 9, -1. So graphically, our curve is going to look like that. And then the last thing we do is add 2, which is going to shift the graph up 2 units. Okay, so we still have our vertical asymptote here at x is equal to -1. when I take the point at the origin and move it up 2 units, that is now at the ordered pair 0, 2. And then the second point, which was at 9, -1, when I shift it up 2 units, is now at 9, 1. Okay, so we can draw our graph looking like so. Again, this has a domain of 1 to infinity. The range is all reals. And the vertical asymptote, it's -1 to infinity. And the vertical asymptote is at x is equal to -1. All right, so hopefully you guys did those problems correctly in class. Okay, let's move on to the last set of problems where the directions here ask us to solve the equation. So we're going to have some basic like exponential and logarithmic equations that we're going to solve. When we get into 7-4, we're going to do much more complicated examples. But this is just basically like getting our feet wet with this stuff. Okay, so first equation asks us to solve for x where the log base x of 4 is equal to 2. Okay, so a good rule of thumb is when you're solving log equations, a lot of times, not always, okay, and we'll talk about like what instances we do this and what instances we don't in the future, but a lot of times you're going to want to rewrite your log in exponential form. So if we rewrite our log in exponential form, the base of our exponent will be the same as the base of the log, so it's x. What the log is equal to is the power, and the argument of the log is what the exponential is equal to. So if x squared is equal to 4, we can take the square root of both sides. That gives us the absolute value of x is 2, which makes x equal to plus or minus 2. If you got that as your answer, it's incorrect. And the reason why you might not recognize, but if we go back to the very start of this lesson, okay, it says the logarithmic function to the base a where a is greater than 0 and a cannot be equal to 1. So when you look at your log base here, it has to be positive and it cannot be equal to 1. So that means that the negative value that we found for x down here, we have to throw that value out. Okay, so the only solution we get here is when x is equal to 2. Okay, let's solve the equation for number 2. Again, we have a log equation. And it's probably best to rewrite this log in exponential form. So natural log, that is log base e. What the log is equal to, that is the exponent. And then the argument of the log, which is this, is what the exponential is equal to. So e to the 8th power is equal to e to the negative 2x power. That's in a great format for us because we have both sides written as an exponential that shares the same base, which makes negative 2x equal to 8 and x equal to negative 4. Okay, let's take a look at number 3. So for number 3, we have e raised to the 2x plus 5 power is equal to 8. Okay, so we have an exponential equation here. Now, if we solve an exponential equation, our goal is to get both sides written as an exponent that shares the same base. And the problem that we have is we don't know how to rewrite 8 as an exponent with base e. Okay, so we only have really one other technique that we can use to work around this problem. And the technique that we can use to work around this is to rewrite this exponential equation as a log equation. So if we were to do that, since our exponent has base e, our log has to have base e as well, so that is natural log. What the exponent is equal to is the argument of the log, and then the power is what the log is equal to. So when we rewrite that exponential equation in log form, it actually puts it into a form where we can solve. Okay, so I can isolate x by subtracting 5, so we get the natural log of 8 minus 5, and then dividing both sides by 2, we get x equal to the natural log of 8 minus 5 all over 2. Okay, last example. Log base 5 of x squared plus 21 is equal to 2. Again, we want to take this log and rewrite it in exponential form. So the base of our exponent is 5, the power is 2, and the argument of the log is what the exponential is equal to, x squared plus 21. So this just transforms into a quadratic equation. So we get x squared plus 21 is equal to 25. I'm going to go ahead and subtract 21 on both sides, which gives us x squared is equal to 4. Take the square root. Absolute value of x equal to 2, which makes x equal to plus or minus 2. Do we use both solutions? The answer is it depends. So when I plug those numbers in the place of x here, the argument of that log function has to be positive. If it is not, then I cannot use that solution as a solution to my equation. So when I plug 2 in, 2 squared is 4 plus 21, that's positive. So that solution works. When I plug negative 2 in, negative 2 squared is 4 plus 21, that's positive also. That solution works as well. So both of those solutions here are good. All right. So that right there should give you enough to be able to complete your homework assignment for 7-2. Again, make sure you guys have that homework assignment done before you come to class on Thursday or Friday. Okay, because that lesson is gonna build on what we discussed here. All right, guys, that's it. Hope you guys have a great rest of your day. We'll see you again on Thursday or Friday.